All right, so in this video, we're going to be looking at how to graph polynomial functions that have real zeros. And we're going to start with some three basic graphs that are going to describe the behavior of how these factors of our larger polynomials are going to behave as they cross through the x-axis. Now, we basically have a linear function y equals x squared, and y equals x cubed as examples of the behavior, depending on whether the factor is repeated one time, two times, or three times. In principle, you can have them repeated more often, but higher degree polynomials will either look very similar to the squared one or the cubic one, and it's not really going to substantially be all that much different if you have zeros that are repeated many, many, many times. So these are the three basic ones. So if you have a linear factor, then when the graph goes through the x-axis at that point, it's basically going to just go through it like a straight line. It's not necessarily at the angle of the slope equals one, but it's just going to go straight through the x-axis at that point. Now, if you have a factor that is squared, so it's repeated two times, or again, any even number of times, it's basically going to look like this. It's going to come down, it's going to bounce off the x-axis, and then it's going to go back up in the same direction. Now, if you have degree 4, degree 6, or whatever, it'll still do this, but it'll look a little flatter around the bounce point. But basically, we don't really deal with a lot of examples like that, but it is still going to, any even degree is going to come down to the axis, and then it's going to come back up off the axis on the same side. It's not going to pass through the axis. And then the other case is the cubic. And if you have a cubic intersect, it's going to go up through the axis. It's going to kind of flatten out as it gets close to the x-axis, and then it's going to continue on through. So when you have a linear factor, you basically just go straight through without any kinks. But if you have a repeated factor with an odd power, it's going to go through, but it's going to go through with a little like kink in the graph. So it's not a straight line anymore. So you can always use these as examples of anything that we're doing. So in an example like this graph, we have it's a quadratic because there's only two factors on it. But as it goes through the two different intercepts, x plus 2 and x minus 3, because each of these factors is linear, it's going to go through the graph at x minus 2, and then it's going to go straight through the graph at x equals 3. So again, these factors are linear, and so around the zero, they're going to behave like a linear function, at least in large part, and they're just going to go straight through straight through the x-axis. Now, if I have a graph like x plus 1 squared, where I have a repeated factor, I have x plus 1 and x plus 1, then it's going to behave like the quadratic when it hits the axis. It's going to come down, and then it's going to bounce back off again. It's not going to go through the axis. Now, when we have these repeated things, we're going to always get some kind of behavior like this. Now, when we're also graphing, we also have to think about what's going to happen when, given the behavior of the leading coefficient. These common polynomials, if they're even, they're normally positive leading coefficient. They're going to go up to the infinity on both sides. But if you have a negative leading coefficient, then a function which is overall an even powered function is going to go down to negative infinity on both sides. If you have an odd powered function, a positive leading term, it's going to start at negative infinity on the left and end up at positive infinity on the right. And then if the leading coefficient is negative, then it's going to switch. So it's going to start at positive infinity on the left, and it's going to end at negative infinity on the right. And that's how we're going to have to orient our graphing as we go through our zeros. So let's look at some examples. So if I had something like this, my leading term is a positive cubic, but it has only one real zero, x squared plus 4. And so the only thing I have to worry about is that it's positive cubic. So it starts at negative infinity, it goes to positive infinity, and it's going to cross through the x-axis at 1. And since this is not repeated in any way, it's just linear, it's just going to go straight through. If I have a function like this, where I have 3 zeros, they're all linear, I'm going to get a cubic again. My leading power is still 1. And so when I try to graph this, I'm going to get something that looks like this. Again, it's going to start at negative infinity. It's going to end at positive infinity. I have 3 zeros. One is at -4, one is at -1, and one is at 2. So again, that's this graph. So here's my -4, here's my -1, here's my 2. And again, if I start at negative infinity, then I go up through the first 0, just like a straight line. I turn around in order to go straight back through the next one, again, as if it were a straight line. And then again, I have to turn around again in order to go back through the next 0 at 2, again, as if it was a straight line, and then off to positive infinity. Now, if I look at an example like this one, x plus 1 squared and x minus 3. So again, keep in mind, this is a cubic with a positive leading coefficient because I have 3 factors here, but this one is repeated. So what am I going to do? I'm going to start at negative infinity and I'm going to go up to my 0, but I can't cross over because it's repeated. So it's going to bounce off like a quadratic square, but then it has to turn around in order to go back through my other factor at 3. And then because it's a positive cubic, it's going to go off to positive infinity. And then I have one more example, another positive cubic, but this time my factor is repeated 3 times. And so I just have 1 0 at 1. And so here, start at negative infinity. I have 1 right here, and then I go off to positive infinity, but it's a cubic repeated factor. And so it's not going to go straight through like I did on my other examples. It's going to approach the origin with a little bit of a kink, and then it's going to go back through on the other side. Now, for a problem like this, we're trying to identify which of these functions that could be. So let's think about this has 1, 2 zeros. One's at 1, one looks like a -5. They're bouncing off the graph. And we have a positive leading term. So they're both going off to positive infinity. Since these are both bouncing off the x-axis, we need squared factors. So that would be this case right here. So x plus 5 squared, that would be this -5, 0, x minus 1 squared, that would be this positive 1, 0. And again, they're bouncing off because the roots are repeated. For something like this, again, this is essentially what would look like if you had a 4th power. It still bounces off the graph, but it flattens out a little bit because it is higher than degree 2. In this case, we have a 0 at -2. We have a repeated one at 0, and then we have another one, it looks like, at 3. And the one that has a repeated 0 at 0 is this graph right here. Again, these are all positive leading coefficients. And so they go all off to positive infinity at the, for large values of x. But we have our -2, 0. This is our repeated zeros at 0. And then this is our 3. For this one, it looks like we have a 0 at 3, but we have a kink in this graph at 0. So that would mean that we need a cubic. So that would be this one. If we look at this graph, I have a 0 here, it looks like at -4, and then I have another 0 at 0. The, the way that this graph looks suggests that maybe there's some kind of this sort of odd kink in the graph suggests that we might have some kind of quadratic unfactorable component to it. So let's actually check that out and see if we can find that. Yep. So that would be this one. So we have a 0 at -4, we have a 0 at 0, and then that weird behavior, because this is a quartic function. It has degree 4, but it has this complex set of zeros that we can't see on the real graph. So they're not causing us to cross the x-axis, but they are sort of affecting the way that the graph behaves. If we look at this one, these are 4 linear factors, 4 zeros. We've got one, it looks like at 5, one at -1, one at 2, and one again at 4. Again, all these just go straight through the graph, so they're all linear. So if we go back, that would be this one up here. And these coefficients out front, they're just to keep the graph from blowing up and being really super large. And then this last example here, again, we have a linear 1 at 2, a linear 1, unrepeated 0 at 5, but we also have this repeated 1, power 2 at 1. And so if we go back to our list of functions, that would be this one. So 2 positive zeros and then a repeated 1 at -1. Now, again, the leading coefficients don't have any effect on the zeros, but they do flip the orientation of the graph. So, for example, again, here's my 0 at 4, -4, 0, and then again at 3. But if I apply a negative to the outside, then I flip the graph around so that, again, my zeros are still 0 because -0 is still 0. They're still at the same locations, but now the orientation, I'm starting at -infinity as I go through the origin instead of starting at +infinity and going through the 0. Same thing for something like this, where I have a 0 at -1, 0, and again at 2. If I apply a negative on the outside, then instead of starting at -infinity for a cubic and going through from the bottom up and then back up, eventually back up again, I would start at +infinity and then come down to go through the origin and then end up again going back down again.